minimum distance. So if you can kind of suss that out of the question, you'll know what formula that you have to look for. And what's constraining this question is that it's nearest to a graph, so it's nearest. This is going to be the constraint. Okay, and this is an instance where a graph or picture definitely helps, so let's do that. Okay, and you can put that into Desmos if you're not sure what it looks like, so I'll do something like this. Okay, and then the 0.40, so this is 0, 1, 2, 3, 4. Okay, and so I'm looking for the point on this graph that is closest to that. Okay, and I'm gonna call that point, I could call it X and then Y, but then if I do that, that doesn't put the constraint in. So I will put the constraint in by calling this X and the square root of X. See how, that it's on that graph dictates the Y value and also gets rid of a variable. So now what I want is the distance between these two, and then if I take the derivative of it and set it equal to 0, that will get me the minimum. Okay, so the distance formula is just the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so I just get, I'm going to write all this as 1/2 because I have to take the derivative, and the square root written as 1/2 is easier to take the derivative. And then I have, so this point here is 4, 0. So I have 4 minus 0 squared. Sorry, let's back up. 4 minus x squared, and then plus 0 minus the square root of x squared. Okay, and then inside there, I'm just going to FOIL that out, and I get 16 minus 8x plus x squared. And then when I square root this one, the square and the square root cancel, and I get minus, let me just show that out. So this is minus the square root squared, which is just going to give me x, so plus x. And then this is to the 1/2. Okay, so now I'm ready. Let's just move this question down. Now I'm ready to take the derivative. So the derivative is equal to 1/2 all of this, which is 16 minus 7x plus x squared to the minus 1/2, and then times the derivative of the inside, which is 0 minus 7 plus 2x, and I'm going to set this equal to 0. So I have minus 7 plus 2x on the top over 2 square root of 16 minus 7x plus x squared. And for this to equal 0, it's where the top will equal 0. So where 7, so x is 7 over 2, and then that makes the y value the square root of 7 over 2. So the closest point would be 7 over 2 and root 7 over 2. And then I'm just going to make sure I answered the question. Find the point. Yeah, good. So I did find the point. Okay, so hopefully I didn't make any mistakes in there. And hopefully you could follow that. So that's an optimization example. All right, so let's do a related rates question. This is a really nice one because there's just a whole bunch of parts going on in it, and we have to interpret the question. Okay, so it says the length of a rectangle is decreasing at this rate Well, the width is increasing at this rate, and I'm pausing the video when the rectangle is 12 by 5. Okay, and then we're going to find the rates of change of area, perimeter, and the length of the diagonal of the rectangle. Okay, so I'm going to draw a picture. Okay, and I'm going to label using length and width, which they told me to do. And then if I know that the length of the rectangle is decreasing at a rate of 2 centimeters per second, that's going to be dl dt. See how the units is telling me that? Centimeters is length and seconds is time. And it's decreasing, so I'm going to make it negative. And then the width is increasing at a rate of 2 centimeters per second. And the when is when L equals 12 and W equals 5. Okay, so now we're going to find the rates of change of area, perimeter, and diagonal length. All right, so area is going to be the formula that links L and W, because those are the rates I'm trying to relate. So that would be L times W. Perimeter would equal 2L plus 2W. And the diagonal length, well, if you think about putting in a diagonal here, then you're just going to use Pythagorean theorem. So d squared equals w squared plus L squared. Okay, so now that I have my 3 formulas that connect L to W, I'm now going to implicitly differentiate, knowing that hidden inside each A, L, and W is some function of time. Because, you know, if you think about making that L smaller and the W bigger, then the rectangle, everything in the rectangle is changing. Okay, so I have dA dt, and then I'm going to be careful because this is a product. So I have first d second plus second d first. Okay, I'm just going to go across and implicitly find the derivative of each of these. Okay, then I have dp dt, so the perimeter changes, and then I have 2 dl dt plus 2 dw dt. And then for this last one, I have 2d d dt. D was an awkward variable to use there. Maybe C would have been better. 2w dw dt plus 2l dl dt. All right, so now I've implicitly differentiated. Now I'm ready to plug in the constants. Let's pick a different color here, purple. So I'm ready to plug in the constants and things when I've paused the video. So I have dA dt is equal to 12 times 2 plus 5 times minus 2. And I have dP dt is equal to 2 times minus 2 plus 2 times 2. And then for this last one, I have 2, and I'm missing the d, dt equals 2 times 5 times 2 plus, sorry, I ran out of space here, 2 times 12 times minus 2. Okay, and then I'm missing in here, but at that instant, when this is 12 and this is 5, I should be able to solve for d, and I get d squared equals 12 squared plus 5 squared, and that actually is 169, so d is equal to 13. Okay. Okay, so now I'm ready to solve. So dA dt is equal to 24 minus 10, 14. And this is going to be in centimeters squared because it's area per second. Okay, and then dP dt, and I mean, we actually squared up here our centimeters. And then I get minus 4 plus 4. So it turns out that at that moment, the perimeter is not changing at all. And so that would be in centimeters per second. Okay, and then the diagonal, I get 26 dt equals 20 minus, what is that, minus 48. And so I get dt is equal to minus 28. And I get minus 28 over 26, and that's going to be centimeters per second. And obviously that reduces 14 over 13. Okay, and then the next question said, which of these quantities are decreasing and which are increasing, and explain how you determine this. So if in the question I make sure to make negative decreasing and positive increasing, then my negatives and positives will continue to mean that. So this is increasing, nothing's happening here, so neither. And this is decreasing. So basically, you know, what we said that we're doing is we're making the length smaller and the width bigger. So like, for example, our next rectangle could have looked like this. So we went from here to here. I mean, that's exaggerated, but that's what we're trying to do. And it's saying when I do that, at the instant when it was 12 and 5, to get to that next instant, the area increases by 14 square centimeters per second, but the perimeter won't change at all at that point, and the diagonal actually decreased a little bit. So hopefully that made sense, and if you have any questions, let me know.